going to see the relation between the regular and angular motion variables. So here we have a particle that is doing a circular motion, something like this. Or actually, let me put it here. So let's say that this strip has a length of, let's say, 7 meters, and let's say that what is the displacement of this particle that passes from here to here. So the angular displacement is just pi over 2. The normal or the regular displacement, that is this, is 1/4 of the circumference of the cycle. So 1/4 of the circumference of the cycle would be 1/4 of 49 p. Sorry, 1/4 of 2p is 2 pi r, that is 2p times 7. So this is pi over 2 times 7. And we will see the displacement, the regular displacement, is always the change or the angular displacement times r. That is because when we wanted to find this displacement, we did 2 pi r, and we will multiply this times this fraction of the total circumference. So what is this fraction? This fraction is delta omega over the circumference of this cycle, the circumference over this, that is 2 pi. So I want to know this is what fraction of the total. So pi over 2 is which fraction of 2 pi. So I want to know pi over 2 is which fraction of 2 pi. So this leaves me with r times delta t. So that's why always the regular displacement would be the angular displacement times the radius. If I know that the displacement was pi over 3 and the radius is 10, I know that the displacement was 10 pi over 3, and that is the only thing we need to do. Now, for the velocity, we know that ds on dt is velocity. What is ds on dt? This would be ds on dt is the same as d omega r in dt. This is what we called the angular frequency. Let's say that this particle does this pi over 2 in 3 seconds, for example. So that means that the angular velocity, the theta on dt, is pi over 2 over 3 seconds. So these are pi over 6 radians. If you would like, you could, if you're confused with radian, you can see our video on radians and the definition of that. So it is just pi over 6 radians. So you know the omega is called the angular velocity, and it is just delta theta over dt. Now, so here we have that the velocity is equal to omega times r, and this is also because we know that the velocity, we want to know in how much the particle moved from what is the velocity of the particle moving from here to here on that interval. So this distance is 2 by r times the fraction of what is this over the entire cycle. So times the fraction omega, theta over 2 pi. This will give me this distance, the displacement, and then I will divide this by the time. So by the time. So I can cancel this, and I have just theta over t, that is the angular velocity, times r. So I have, one is this, the other is that velocity will be equal to the angular velocity times the radius. Now if I take the second derivative of the displacement in time, this is the acceleration, and this will be the omega r on the t. This will be, this is called the angular acceleration times r. Actually this acceleration is the tangential acceleration, so it is the acceleration when the particle is here. This acceleration sub time is this. When the particle is here, is this acceleration. So it's the tangential acceleration. Now, there is also other acceleration, that is the centripetal acceleration, and that is the acceleration of the force that is pulling the particle towards the center. So this is the acceleration, the centripetal acceleration, and it's always perpendicular to the tangential acceleration. So there is here also something that we need to say about acceleration. In acceleration, we have the tangential acceleration. For example, here we have this tangential acceleration, and we have here the centripetal acceleration, that is always the same, the magnitude is always the same. So these are the components of the acceleration vector. This will be the vector, the resultant vector. Which components are the tangential acceleration and the centripetal acceleration? So the acceleration squared would be equal to the centripetal acceleration squared plus the tangential acceleration squared. And the tangential acceleration is alpha, the angular acceleration times time, and the centripetal acceleration, we derived this on a previous video. The centripetal acceleration is either p squared divided by r or omega squared times r. Now in the next video we will relate more angular variables with regular variables like momentum, and we will see linear momentum, not to be confused with moment of inertia. That has nothing to do with time nor with momentum.